Enzymes are some of the most incredible molecules on the planet. They're essential for life as we know it. You see, life is all about chemical reactions, and enzymes enable much slower reactions to go fast, allowing our cells to quickly respond to environmental changes. Many enzymes are proteins, or simply strings of amino acids, that spontaneously fold into a three-dimensional shape. Their shapes are critical for their ability to act as catalysts, so it comes as no surprise that biologists are often very interested in learning the shapes of enzymes. But how do we study shape? Often, we simultaneously probe a collection of enzymes and get a signal that correlates with shape. But there are a couple of problems with this approach. First, the signal that we get is an average of all the molecules that we're looking at. So any shape that makes up a small part of the population will be averaged out. For example, the average position of people in a crowded room where all but one are sitting is very close to the seated position, even though a small part of the population is in a very different conformation. The second problem is that we can only measure shapes that our signals are sensitive to. Take, for instance, a ball and a disc. From one angle, they look almost identical. But if we turn them slightly, we can see that in reality, they're very different shapes. We must therefore choose a measurement technique that allows us to discriminate between the shapes an enzyme can adopt. My thesis work focuses on adapting force as an alternative measurement of shape to study an enzyme we thought we had already figured out. The enzyme I study is shown in blue and orange. It is present in many organisms and is responsible for maintaining the energy balance inside cells. Studies have indicated that there is a small part of the population of this enzyme that doesn't work very well, and it may be because the orange section is unfolded. I've attached molecular handles, like tiny tweezers, to the ends of the enzyme and pulled on it to see if I can use the unfolding force to distinguish between these two different shapes. I've discovered that the unfolding force of the entire molecule correlates very strongly with the fraction of molecules expected to have their orange section unfolded. With this new technique, I've also been able to verify that the partially unfolded population makes up a small but significant fraction of the total molecules in the collection. My work demonstrates that we need to change the way that we think about this enzyme by taking into account the small, less effective part of the population and trying to understand its role. A subtle change in enzyme shape can have a dramatic impact on its function. Therefore, if we want to better understand human health, we need to take a closer look at enzymes that may have hidden shapes. Thank you.